So this is lecture 14. And it's just to review, answer questions about anything in the course, and in particular, anything from the review sheet.
Let's see. Excuse me, Professor, can we possibly go through, let me see which question. Just review. Can we go over number 5 on the final review?
Okay. Final review. Problem 5. So we have primes P equal to 5, Q equal to 11, and E equal to 3. So PQ is 5 times 11, or 55, and P minus 1, Q minus 1 is 4 times 10, which is 40. And the GCD of E and of 3 and 40 is 1. There's not really anything to prove, because 40 is divisible just by the primes 2 and 5. What's the smallest positive integer D? You want to solve DE congruent to 1 mod P minus 1 Q minus 1. So E is 3. You want to solve 3D congruent to 1 modulo 40. So you can do it the long way or the short way. Short way is just to see how to solve the problem. You notice that 3 times 13 is 39, is the same as minus 1 mod 40. So 3 times minus 13 would be plus 1 mod 40. So D can be any number congruent to minus 3, minus 13, or 27 mod 40. And you can check 3 times 27 is 81, which is 1 plus 40 times 2. So D equal 27 is the smallest positive solution. And then you want to find the smallest positive integer x. You want to find x such that x cubed is congruent to 52 mod 55. So there's a hint that says, look at proposition 3.5. So let's see, what is proposition 3.5? Proposition 3.5 says, okay. The proposition 3.5 says that if DE is congruent to 1, mod P minus 1, Q minus 1, then the congruence x to the E congruent to C mod PQ has the unique solution x congruent to C to the D mod PQ. So this seems to fit this situation exactly because E is equal to 3.
Professor, can you move the paper down a little bit? Thank you.
E is equal to 3. So, and C is 42. So just looking at this proposition, it says x cubed is congruent to 52 mod 55 if and only if x is congruent to C to the D. D is 27. So 52 to the 27 mod 55. Of course, we still have to figure out what this is, but it's somewhat easier if we notice that 52 is the same as minus 3. So that's minus 3 to the 27 mod 55. And minus 1 to an odd power is minus 1. So congruent to minus 3 to the 27 mod 55. So we have to figure out what this might be, right? But the reason for proposition 3.5, the proof of this is that if we take, so C to the D is congruent to X to the ED, we're just raising this to the power D, but ED is 1 mod P minus 1 cubed minus 1. So this is congruent to X mod PQ because anything to the power P minus 1 Q minus 1 is 1 mod PQ. So you just have to play with this a little bit and compute what it is. So that's just some arithmetic.
Yeah, so you find D and then you plug it in because you have C and everything. You plug it into that equation and then solve for it, right, Professor?
Yeah, I mean, it's exactly this. So if you look at the proposition, E is equal to 3, and you're solving x cubed. This is x to the E mod PQ. X to the E congruent to C. E is, in this problem, E is, the exponent E is 3, the number C is 52, and PQ is 55.
Okay. Okay, so and Professor, like you said, there are gonna be a couple, I guess, like, will this like be like one of the main parts of the exam, like question like this, or is it mainly gonna be like you said, like mostly like I guess like the cryptographic methods in terms of like
Well, it's mostly cryptographic methods,
Mhm.
but those methods are basically all
Yes.
applications of the number theory we developed. So there will be a little bit of this sort of number theory on the final as well.
Okay. I understand, Professor. Mostly Professor, can we do one that has like multiple parts, like number like number 4?
Let me find number 4. So in problem 4, we have P equals 31. And we want to find integers x and y such that 7x plus 31y equals 1. So let me show the method that always works. Though in this case, so a method that always works is you apply the Euclidean algorithm to find the greatest common divisor. So 31 is 7 times 4 plus 3. 7 is 3 times 2 plus 1. So 1 is 7 minus 3 times 2, which is 7 minus 3 is the same as 31 minus 7 times 4 times 2. So this is 7, and here I have 8 times 7. So 9 times 7 plus 31 times minus 2. Because this is really just 63 minus 62. So that's the first part. And the second part is instead of 31, use the number 7. It's 30. So if you take 30 and divide it by 7, this is again 7 times 4 plus 2. 7 is 2 times 3 plus 1. 3 is 1 times 3. So 1 is 7 minus 2. What is 2? 2 is 30 minus 7 times 4, and it's 2 times 3. So how many 7s are there? I have 12 plus 1. This is 7 times 13 plus 30 times minus 3. And again, you check, this is 91 minus 90. So it certainly is equal to 1. Okay. Any question about that?
No, Professor.
Okay. So in part B, we want to solve the congruence DE congruent to 1 mod P minus 1. P is equal to 30. E is equal to 7. So we want to find 7D congruent to 1. Mod, let's see, P is 31, P minus 1 is 30. Well, if you look at this, this says that 7 times 13 is congruent to 1 mod 30. And this solution is unique mod 30. So between 1 and 30, the only solution is 13. The answer is D equal 13. And we want to solve in part C, x to the 7 congruent to 24 mod 31. So we know that if x is any number not congruent to 0, mod 31, then x to the 30, x to the p minus 1 is congruent to 1, mod 30. So let's see. If I can find a number such that so we just proved that let's see, 7 times 13 is congruent to 1 mod 30. So x to the 7 times 13. So if x to the 7 is congruent to 24 mod 31, that's the case if and only if x to the 7th to the 13th is congruent to 24 to the power 13 mod 31. X to the 7 times 13 is congruent to x mod 31 because 7 times 13 is 1 mod 30. So the solution is x congruent to 24 to the 13th mod 31. So I guess we have to figure out what that is. 24 is the same as minus 7 mod 31. And minus 1 to the 13th is minus 1, so this is minus 7 to the 13th mod 31. And so you have to look at the powers of 7 mod 31 and see what 7 to the 13th is. And that's just a calculation. In part D, we want to prove G equal 2 is not a primitive root mod 31. So if you start to look at the powers of 2, 2, 4, 8, 16, 2 to the 5th is 32, is congruent to 1 mod 31. So 2 has order 5 mod 31. So it's not a primitive root. It has to be that the smallest power of a G that's congruent to 1 mod 31 is the 30th power in order for the number. So 2 not a primitive root. What about 3? So let's look at the powers of 3. 3 to the first power is 3. I'm doing everything mod 31. 3 squared is 9. 3 cubed is 27, which is the same as minus 4 mod 31. 3 to the 4th is 3 cubed times 3. So 3 to the 4th is 3 times minus 4, which is minus 12. 3 to the 5th is 3 times 3 to the 4th. That's 3 times minus 12. That's minus 36, which is minus 5. 3 to the 6th is 3 times 3 to the 5th, which is 3 times minus 5, which is minus 15. Or 61. Minus 15 is the same as 16 mod 31. 3 to the 7th is 3 times 3 to the 6th is 3 times 16 is 48 is 17. 3 to the 8th is 3 times 17 is 51, which is 20. By the way, so if 3 to the k is congruent to 1 mod 31, then k so if the order of 3 is k mod 31, if the smallest positive power of k such that 3 to the k is congruent to 1 mod 31, then k has to divide 30, because we know 3 to the 30th is certainly congruent to 1 mod 31 by Fermat's theorem. So the order of k mod 31 is a divisor of 30. So what are the divisors of 30? There are a lot of them. 1, 2, 3, 5, 6, 10, 15. So let's look at what is 3 to the 10th? Well, the 3 to the 9th is 3 times 3 to the 8th, which is 3 times 20, is 60, which is minus 2 mod 31. So 3 to the 10th is 3 times minus 2, which is minus 6. We still haven't gotten to 1. 3 to the 5th is minus 5. So 3 to the 15th, which is 3 to the 5th times 3 to the 10th, is minus 5 times minus 6, which is 30, which is minus 1 mod 31. So we just proved 3 is a primitive root modulo 30, because the order of 3, modulo 31, the order of 3 mod 31 is a divisor of 30. So the divisors of 30 are numbers, they're the numbers up to 15, and if none of the numbers up to 15 that divides 30 is the order of 3, then the order of 3 must be 30, and so 3 is a primitive root. That's the argument that's used. And we also want to prove 5 is a primitive root mod 31. Let's see. So again, all these things are just calculations. They're actually quite interesting calculations. So what is the order of 5 modulo 31? It's equal to 30. That just means if and only if 5 is a primitive root. It's the definition of a primitive root. So we have 5 to the first power is 5. 5 squared. In fact, what are the divisors of 30? 1, 2, 3, 5, 6, 10, 15, and 30. So the order of 5 is one of these numbers. If it's none of these, it has to be 30. So 5 to the first power is 5. It's not 1, so we can cross that out. 5 squared is 25, or minus 6. It's not 1. We can cross out power 2. 5 cubed is 5 times 5 squared. 5 times minus 6 is minus 30. That is 1. So is that right? 125. Yeah. So there's a mistake there in the problem, because 5 is not a primitive root mod 30. 5 cubed is 125, is 4 times 31 plus 1. So 5 has order 3 mod 30. So that's not Good thing. And the last part was to compute some discrete logarithms. 7 is a primitive root. Sorry, 3 is a primitive root. Mod 31. And we want to compute the log of 17 to the base 3, mod 31, and the log of 2 to the base 3, mod 31. So let's see, on the previous page, I had computed some powers of 3. So let me start to make a list of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is K. And this is 3 to the K, mod 31. So 1, 9, 27, 3 to the 4th was minus 12, which is 19. 3 to the 5th was minus 5, which is 26. 3 to the 6th was 16. 3 to the 7th was 17. Aha. So three to the 7th congruent to 17 mod 31 means the log of 7 to the base 3, log of 17 to the base 3 is 7. Let's see, what is the log of 2 to the base 3? I haven't gotten...
For instance, the base 2 logarithm.
Oh. So, let's see. 3 to the 8th, I had calculated was 20. 3 to the 9th was minus 2. Actually, I calculated 3 to the 15 was minus 1. So 3 to the 9th is congruent to minus 2 mod 31. And 3 to the 15th is congruent to minus 1 mod 31. Then 3 to the 24th power, which is 3 to the 9th times 3 to the 15th, is minus 2 times minus 1, which is plus 2 mod 31. So the logarithm of 2 to the base 3 modulo the prime 31 is equal to 24. So that is the series of calculations for that problem. Any questions about that?
No, thank you.
Thank you, Professor, for explaining it for us.
I'm sorry, and you said something, but the sound was garbled.
Oh, I said thank you for
Oh,
explaining
okay,
it.
sure.
Fatima, do you have any questions to ask? Because I probably just have one more, but
No, I'm good. Thank you. You can ask.
okay. Let's see. I actually just have two more questions and then that's it, Professor, because I pretty sure that I could solve the rest of them on the review.
Okay.
The first one would be the RSA digital signature for number 14. I just want to like make sure that I know the entire process. Just to clarify.
Okay. Let's see, problem 14.
Just for clarification.
Okay. So the RSA digital signature. So Bob chooses the primes P equal 5, Q equal 11. So N, which is PQ, is 55. P minus 1, Q minus 1 is 4 times 10, which is 40. And the exponent E for encryption, E equals 3, satisfies that the GCD of E and 40 is 1. So that is okay. And so you compute D, where 3 times D is congruent to 1, mod 40, which we did previously. So D is 27. And you can, if you have the document 343, you want to sign the document. So you want someone to know that this message is really coming from you. Your signature is capital D to the.
Professor, could you please move down the paper a little bit?
Yeah, okay.
Thank you.
It's exactly what's written in the problem. So this is 343 raised to the power 27 modulo 55. And that's S. Now, I mean, 343 is actually 7 cubed. So you can also say this is 7 cubed to the 27th, or 7 to the 81st power, mod 55. And 7 to the 40th is congruent to 1, mod 55, because P minus 1, Q minus 1 is 40. So anything relatively prime to 55 raised to the 40th power is going to be 1. So this is, in fact, 7. It's just 7. Right? This is 7. This is 40 times 2 plus 1. That's what 81 is. So that's 7 to the 40th squared times 7. 7 to the 40th is 1. This is just 7 mod 55. So the signature that you send is just the number 7. And you verify the correctness of the signature by computing S to the E. E is equal to 3. So that's 7 cubed. 7 cubed is 343. So it's exactly the D.
Okay, move down the paper. So it's like basically you to verify it, you take S to the E, which is 7, 3, and then make sure.
Right. So the point is that
Mhm.
the person sending the message wants to, the person receiving the message has to know that it's not a fake or a bogus message. It's really coming from the person who claims to be sending it. So you're sending the document and you're sending a document and you want to sign it. in such a way that the person who receives it can tell that you're the signer. You actually sent it and no one else. So you're the person sending these messages. So you announce the number 55, PQ, and E equal 3. Now, because you know that you know how to factor P and Q, N into the product of P and Q, you can compute the D such that D times E is congruent to 1 mod 40. So you're the only one who knows the D. So you take your document, you raise it to the power D. The person who gets it raises it to this public key E. And if it turns out to be D, they can believe you sent the message because you're the only one the sender is the only one who knows the D. And if you raise your message, your document to a power other than D, then raising it to the power E will not give you the 343, which you're allegedly sending. So you're
Okay,
sending
Professor.
this document, and the person getting it has to know that you really sent it, and it's not a fake document from your enemy to confuse you. So this signature method, this is the RSA signature, which is almost like the RSA crypto system, but sort of backwards. So in the encryption system, anyone can send you a message. Anyone can encrypt the message and send it, but you're the only one who can decrypt it. Here, you're sending the message, and you're sending your signature, and you're the only one who can send that signature because you know the number D.
Okay. Yeah, makes sense.
I mean, again, the text is very clearly written, I think, and if you just read the first couple of pages of the chapter on the digital signature, it should become clear.
No, I understand, Professor. I just wanted clarification. I just the only part that like I had a little confusion on was how to verify, but like you just clarified it again for me. So
Right. Yeah. But it's also exactly what it says in the problem, right? It's like, but anyway, sometimes it's better to hear it. And did you have one more question?
yeah, the last question I had would be, let me see here. Would be like number 3 and like prove the congruence and stuff like that. Number 3 is my last one.
So in problem 3, you have a prime P, you have an integer E, where the GCD of E and P minus 1 is equal to 1. So if the GCD of E and P minus 1 is 1, that means that their numbers X and Y such that EX plus P minus 1Y equals 1. Right? I mean, that's from the Euclidean algorithm, right? You can, if two numbers are relatively prime, some linear combination of them is 1. So you just let D equal to the number X. And then D times E is congruent to 1 mod P minus 1. And we know that this is Fermat's little theorem. If A and P are relatively prime, then A to the P minus 1 is congruent to 1 mod P. So suppose you have x to the e is congruent to c mod p, then x to the ed or x to the de is congruent to c to the d mod p. But de is congruent to 1 mod p minus 1. So de is equal to 1 plus the multiple of p minus 1. So x to the de is x to the 1 plus p minus 1 times k is x times x to the p minus 1 to the k, but x to the p minus 1 is 1, so this is congruent to x mod p, and is congruent to c to the d. So the solution of, if you want to solve x to the e congruent to c mod p, you let x, so the solution is x congruent to c to the d mod p. So this is all using Fermat's little theorem, or more, here we're just using Fermat's little theorem. The general rule is that if you have a modulus m, and if the greatest common divisor of a and m is 1, then a to the power phi of m is congruent to 1 mod m, where this is the Euler phi function. And we use this in the case, so if m is p, phi of p is p minus 1. If m is p times q, phi of m is p minus 1 times q minus 1. That's what we use in RSA. And in another problem we had a moment ago. All right. Any questions about that?
Nope, that's
Okay. Again, last Zoom session I have is at 7 this evening. If you have any more questions that come up during the day, you should certainly log on and ask.
all right. Thank you, Professor. And
Okay. There you go.
is there one more time? What's it? Is there only like one time, right, for this final? Right, it's only at 4.
It's at 4, but some people have a conflict with other classes. So it's also possible to take it at 7, from 7 to 9.
I'm probably take it around like 4. But
But
so
I
from
sent
4,
out an email about that. Anyone who cannot take it at 4 and wants to take it at 7 has to send me an email and let me know in advance.
okay.
But the exam time is 4 to 6.
Right. Thank you, Professor.
Thank you.
Okay. Okay. Right. Bye all.
Bye.
Bye, Professor. Thank you for a great semester.
Thank you.